Math and Beats. In this video, we are going to look at what is called the first derivative test, and this is going to be a means for which helps us identify local extrema. Let's take a look. All right, our goal, like I said, is we're going to not only identify local extrema, but also classify them. So, when we find this local extreme point, is it a local min or max based on using the first derivative? That's the goal of this video. So we're going to focus on increasing and decreasing functions in corresponds with the derivative, and kind of combining some ideas, we'll be able to come up with what is called the first derivative test. So let's just remind ourselves about increasing and decreasing functions here real quick to get going. Let's suppose that you got a function and it's defined on some open interval I, and x1 and x2, just some numbers that both belong to I. Assume that x1 is the smaller of the two numbers, so it's located to the left on the x-axis. Then, if you have that for all values of x1 and x2 in this interval I, this open interval, that we also have the value of the function at x1 is less than the value of the function at x2, then this is what it really means to be increasing on an interval I, an open interval. So picture showing just an increasing function here. Here is some function f of x. Here's some arbitrary x1 and x2 values on some interval, maybe like, I don't know, who knows, maybe like that is our interval I there, for instance. And what we're saying is that no matter which x1 and x2s you pick, as long as x1 is to the left of x2, then the value of the function right there at x1 will always be less than the value of the function at x2. And so really all that means is as you move left to right over this interval, the values of the function are getting larger. Likewise, as a reminder, if for all x1 and x2 in our interval I, we have rather that the value of the function at x1 is bigger than the value of the function at x2, then this is how we describe a decreasing function over an open interval. And here is a picture to depict such a situation. And as we can see, pick some x1 value, the value of the function right there, f of x1. And no matter which ones we pick, as long as x1 is to the left of x2, that value of the function at x1 should be less than, greater than the value of the function at x2. Right, so all that's really saying is the function's output values are decreasing, right? They're getting smaller in value as we move left to right over the interval. Now, that was our little refresher. Notice that if you have any value of x in this interval I of consideration, then some things happen. If the derivative of the function at x is bigger than 0, then of course f is going to be increasing on that interval. And likewise, if you're increasing, the derivative is going to be positive, right? Because the slope is going to need to be positive over that particular interval for the function to be increasing, because a positive slope says that our instantaneous rate of change is also going to be positive, meaning immediately as I move to the right from this point of tangency, I will be increasing in value. So positive derivatives tell us the functions are increasing, and in particular, if we have the conditions that we had in the pictures before this, then of course this would be happening at all values of x over the interval. Likewise, if the function's derivative is negative on the interval, then the function of course will be decreasing, and this is because of course the slope of the tangent line at any given point over the interval will be a negative number. And so some of this we've already kind of investigated, but now we're going to formally state it as we have just done as we need these ideas to develop our first derivative test. How so? Well, first, now that we've gotten that out of the way, right? Positive derivatives, function's increasing. Negative derivatives, the function is decreasing. Then we're going to look at a few graphs involving local extrema so that we can get an idea of how this first derivative test is going to work. Let's take a look. Now remember, just as a reminder, we've already previously established in another video that a local extreme point has to occur at a critical point. Okay, so we're going to look at some critical points here, and we know that if you have a local extreme point, there's also a critical point at that location. And now we're going to involve the concepts of the first and second, or the first derivatives. Okay, here's just a parabolic function. We have our critical point right there, and in particular at that location f prime of c here is 0. We have a critical point of type 1. Notice that at this location we also have a local extreme point, in particular a local max point. So at x equals c, f has a local maximum, right? Has a local extreme point. And the derivative is 0 there. That's one way we can have a critical point. And then you notice, as we move from left to right towards x is equal to c, all the way down there, everything to the left of c in this case, the derivative of the function is bigger than 0, and that's true for values of x less than c, right? All my tangent lines over there are going to have positive slopes. And then as we pass through c, right, the derivative is 0, and now to the right of x equals c, the function is decreasing. And hence over here, f prime of x is going to be negative, and this is for values of x bigger than c. So part of this example right now is to help us notice that we have a local maximum point at x is equal to c. And the derivative is changing signs from positive to negative at x equals c, while simultaneously at x equals c we have a critical point. The derivative is changing signs in this particular order from positive to negative. So let's just take another look at another example here. This example, this next graph, we have a function k of x given to us, and we can see that at x is equal to c, right down here, k of x has a local minimum value. And where's that occurring? At x is equal to c here. Moreover, we have a local extreme point, so we know that we have to have a critical point. In this case, k prime of c is undefined, right? It's a critical point of type 2. Now, what about our derivatives? Well, let's first look at this function's derivative to the left of c. As I'm approaching x is c from the left, we can see that right over here, k prime of x is going to be negative. It's decreasing function, and that's true for values of x less than c. To the right of c, we can see right over here that k prime of x is going to be positive. The function is increasing over there for values of x larger than c. And again, we see that there is a change in the function's behavior at this local minimum point. In this case, the derivative is changing signs from negative to positive, meaning that the function is changing from decreasing to increasing. And we had a local minimum point. So again, there's this change in signs of the derivative. A couple more here. Here's one that is discontinuous at x is equal to c. This function y is equal to g of x here. But Notice that if I draw a little open interval around C, arbitrarily tiny if we wish, and I go up to the graph of the function here, then all values that are not at C are going to be bigger than or equal to the value of this output here at C. So in this case, at x equals C, G has a local minimum point for that reason. Also, G prime of C is undefined, right? The derivative does not exist at x equals to C. We have a discontinuity there. And so this would be a critical point of type 2, of course. But then again, look at the behavior of the derivative and the function as well. As I get close to x is C from the left, again, we can see right here that G prime of x is positive for values of x less than C, right? The function is increasing as we get close to C from the left, and therefore the derivative must be positive. As we move to the right of x is C, this function is decreasing. So over here, G prime of x is going to be negative, and that's for values of x that are greater than C. I had to rewrite that C up there. I had a 0 for some reason. So the point is that our derivative is once again changing signs at this local extreme point. And in this case, it is changing signs from positive to negative. And so what must be happening? Well, does this always happen? Let's take a look at one more here. And so here is this function h of x. Okay, now this function, we can see that there is no local extreme point right there. No local extreme point, since to the left of C, the values are less than C, or the h of C here, and to the right of C, the values are bigger than h of C. So there's no local extreme point. Moreover, as I move along my graph from the left to the right at C, and also to the right of C, we can see that, in fact, h prime of x is always going to be positive. And this is true for values of x that's not equal to C, because at x equals C, we have a horizontal tangent line here, and the slope is actually 0. So in this case, we actually don't have a sign change at x is equal to C. Moreover, we don't have a local extreme point there. So what's the dealio? Well, this is going to be something that allows us to conclude what the first derivative test is. So here it is. Here's the first derivative test. Now, important here, some things that we have to assume going on is that, first of all, f of x has got to be assumed to be continuous on an interval I that contains this value of x is equal to C, where x is equal to C is a critical point for the function. So again, take note. Assuming we have a function that's continuous, and then we got it continuous over some interval that contains a critical point, x is equal to C. Assuming that's all true, then if the function's derivative, f prime, changes its sign from positive to negative at x is equal to C, then we must have that at x equals C, there's a local max point. Just think of a picture that looks like that, right? Local max point right there. The function's derivative is changing from positive to negative at that point, and the function is continuous. If, on the other hand, the derivative changes sign from negative to positive at x is equal to C, then the function must have a local minimum point at x is equal to C. So you draw a little picture, looks like that, right? The derivative is changing from negative to positive at the location x is equal to C here, and the function is continuous. We also saw an example a moment ago in which, well, if the function's derivative doesn't even change signs at x equals C, so it doesn't change signs here, then there is no local extreme point. This function does not have a local extreme point at x equals c. So basically, you have one of two things happening for a local extreme point. Local max, the derivative is changing signs from positive to negative. Local min, the derivative is changing signs from negative to positive. And if that sign change does not happen one way or another, there is no local extreme point for the function, all under the assumption, of course, that the function is also continuous. Now, I just want to scroll back up real quick here because we saw an example earlier, this one, in which the function actually was not continuous, right? It was discontinuous at the location of x is equal to c. And you notice there that the function's derivative changed from positive to negative at x equals c, so there was still a sign change in the derivative. However, in that case, we actually had a local minimum. And that's can happen, obviously, it happens right there. But when we talk about the first derivative test, we're only talking about functions that are continuous at their critical points. And then that first derivative test will work flawlessly. All right, so I just want to point that out. Now, how do we use this first derivative test? Well, assuming all the conditions are met, just apply the first derivative test to a function. First, you got to find all critical points of the function of the interval of concern. And so, right, we got to find the derivative and figure out where it's either equal to 0 or where it's undefined, assuming that, of course, those critical points are in the domain of the function. And then from there, what we do is we perform sign analysis on the derivative, applying the first derivative test to determine and also classify all local extrema that this function may have. So we're going to see a couple of examples here of how to do this before we end the video. Whoa. All right, here's an example. Let's find and let's also find and classify all local extrema for each of the following functions, and the intent is to use the first derivative test. And now when we say classify, that means, figure out whether it's a local max or local min point. Here's this first function. F of x is this polynomial 2x cubed plus 3x squared minus 12x plus 1. So the first thing we got to do, we're trying to find all the local extrema. So let's find the derivative of this function, which is just 6x squared plus 6x minus a 12. And notice that's the same as 6 times x squared plus x minus a 2. Now, this is a polynomial function, so it's never going to have a derivative that is undefined. Rather, it can have a derivative which is equal to 0. And in this case, if we went ahead and factored it further, we would get 6 times x plus 2 times x minus 1. And, of course, that's equal to 0 if the values of x is either 1 or x is negative 2. So notice that these are both critical points of type 1, right? Our derivative is 0 there. And both of those values of x are in the domain of this function because this function is a polynomial and it's defined for all real numbers x. Moreover, polynomial functions are continuous over their domains. So this function is also continuous for all real numbers x. And thus, we can say that for sure our first derivative test will apply to these values of x. So let's apply that first derivative test. And that is, we go and we perform sign analysis on the derivative here. So say here is the outputs of f prime, and here are corresponding values of x. Say here is negative 2, and here is x is 1. We know that the value of the derivatives at this location are 0. And our job is to figure out whether there is sign changes in the derivative at these locations to classify the extrema, the local extrema. So we just do our sign analysis. Down here to the left of x is negative 2. If I plug in a gigantically negative number, then 6 times a negative is going to be a positive, so the derivative is positive over there. If I say plug in x is 0, notice if I plug in 0 to my derivative, we get negative 12, so the derivative is negative in there. And if I plug in a massively gigantic positive number to the right of 1 up here, then we just get a positive number. And so there's our sign analysis on f prime, our derivative here. And we can see that there is sign changes in the derivative at x is -2 and at x is equal to 1. And in particular, at x is -2, the derivative changes from positive to negative. And at 1, it changes from negative to positive. So at x is -2, we can expect some kind of hump like that. And at x is equal to 1, some kind of hump like that. And that's really what the first derivative test allows us to conclude. And thus, at x is equal to -2, this function f of x here has a local max as f prime changes from positive to negative. Also, at the location of x is equal to 1, this function f of x has a local minimum, just write min, as f prime changes from negative to positive. And there's our first derivative test at use. Let's look at one more before we wrap it up. Okay, here's a function g of x. Let's call it 4x to the 3/5 minus x to the 8/5. And this function, because we have odd roots in both terms, is defined for all real numbers x, and it is not piecewise defined. It's a combination of power functions here, and it is also continuous for all real numbers x. And thus, if this thing has any critical points, then the first derivative test will be applicable. Let's go ahead and find the derivative. G prime of x here, it's going to be 4 times a 3/5 times x to the -2/5 minus an 8/5 times x to the 3/5. So let's clean that up, because we're going to have to figure out where it's equal to 0 or if it's undefined. I'm going to go ahead and factor out a 4/5 x to the -2/5 from both of the terms. And what I'm left with is a 3 minus a 2x. And so notice, of course, that's the same as writing 4 times 3 minus 2x, all divided by 5 times the 5th root of x squared. And so it tells us that g prime of x is equal to 0 if x is equal to 3/2, and g prime of x is undefined if x is equal to 0. So we have two different types of critical points here. And the first one at 3/2 being a critical point of type 1, where we have some kind of smooth situation. And at g prime of 0, we have some type of critical point of type 2 for which the derivative is undefined. Regardless, we can still do our sign analysis to figure out whether we have extrema, maximal or minimal local extrema here. So here's another sign chart for g prime in terms of x. Maybe here is x is 0. We know that at that location, I'm just going to use like a u like this since the function's undefined. And at 3/2, I know my derivative is 0. So we do some analysis with the signs here, right? So let's use this form right there for g prime. If I plug in, say, x is a gigantically negative number, okay? So if a negative number is put in up here, then that's going to be a positive, 3 minus 2 times a big giant negative. In the denominator, I'm squaring that negative number and then taking the 5th root. So over to the left of x is 0, we have that our function's derivative must be positive. Somewhere in this interval is x is 1. If I plug that in there into the function, then in the numerator I have a positive, and in the denominator I also have a positive. So in fact, it's positive in there. And then pick a giant positive number to the right of 3/2. Now we're going to have a negative, because in the numerator, that'd be a giant negative divided by a positive in the denominator. So we see our sign changes, and in fact, in this particular situation, what we see is that at x equals 0, there is no sign change in the derivative. It's positive to the left of 0, and it's positive between 0 and 3/2. So there's no local extreme point at x is 0. So right here, no local extreme point at x equals 0, since the derivative does not change signs. However, at x is equal to 3/2, we have that the derivative does change signs from positive to negative. So it's got to look something like that. So at x equals 3/2 here, g has a local max, as again, the derivative changes signs from positive to negative. And there you go. That's the video. So part of this video, of course, just to recap, was to remind us of increasing and decreasing functions, and then how that relates to derivatives, right? Derivatives are positive when they are increasing, they are negative when they are decreasing. And then we looked at various situations where we had local extrema, and that allowed us to come up with what's called the first derivative test here. So this isn't the end of classifying extrema. In fact, there's more to this game. And the next video will go further into that, including concavity and second derivatives. Until then, it's Matter Beats. See ya.